drawing, this was describing the voltage-gated sodium channel and the three states of this channel with regard to the two gates on this channel. Okay. So we described starting off at rest, which was -70 millivolts. And we said that if we had enough of a graded potential to get to that threshold of -55, we would change the state of this channel by opening up the activation gate, and this would create two separate events, right? So one is that we open the activation gate, but there's a 1 millisecond signal that will close the inactivation gate after that time has elapsed, okay? And then finally, in the third phase of this channel, we described that at +30 millivolts, the activation gate is still open, but because of this initial signal here, the inactivation gate is now closed. And so in this state, the channel is said to be closed and incapable of being opened. That's because the inactivation gate specifically is closed. And so we want to describe this channel relative to something that we're going to speak about today. Okay, this is called the absolute refractory period. So this state of the channel represents the absolute refractory period. Okay, we're going to describe what this means, but during this phase, or when the channel is in this state, we cannot fire another action potential. Okay, really, really important. So the absolute refractory period means that there is a closure of this inactivation gate. So even if we had depolarizing stimuli, even if we had graded potentials, because of this incapable of being opened state, we cannot physically fire another action potential until we get back over here to rest. Okay? And we'll go on to describe that a little bit further today. All right, so let's proceed. Okay, so that was the sodium channel, a little bit more complex. The potassium gated channel is a little bit simpler because there's only one gate on this channel. And at around +30 millivolts, that is the voltage sensitive level, or the membrane potential at which this potassium channel will open. And when this channel opens, potassium rushes out of the cell according to its ECDF. This helps to make the membrane potential repolarize or get back down to rest, right? We got all this positive potassium moving out of the cell, and it's leaving behind this negative environment. And so the membrane potential begins to reapproach that resting value of -70. Okay. Now, important to note here, there's one gate, but that gate is voltage and time sensitive. So much like the inactivation gate on sodium, the potassium channel gate is both voltage and time dependent. Okay, so at that -55 value, at that -55 threshold, there's also a 1 millisecond delay to then open the potassium channels at the same time that we close the inactivation gate on sodium. Okay, so there are two timed events happening here, and that's really important. That's why we end up with that refractory nature of the action potential. So after that 1 millisecond that we said, at -55, that threshold value was met, and there were two timed events. The first 1 millisecond timed event is to close the inactivation gate on sodium. But then the second 1 millisecond timed event is to open up the potassium gate. Okay. Now this creates a negative feedback loop because we're now moving back to our resting membrane potential. In other words, back to our set point. Okay, that -70 value. So let's describe what's happening here. So now excitable membranes have this ability, right? This action potential ability. And an action potential is what? What can we describe an action potential as? In terms of the broader sense, in terms of the function of it. What is an action potential really doing? So in a cellular level, it's simply a depolarizing event on a neuron or another excitable cell, such as muscle. But in the broader sense of things, an action potential is simply a means of communication, right? This is how neurons speak to each other. This is how neurons speak to muscle. This is how we do things like walk and talk and move and think. Memories, these are communicated via one neuron to the other, and this is how they communicate. This is their language, so to speak. Action potentials. Okay, so that's the big picture of what an action potential is. Although we've kind of been zooming in on the cellular events of an action potential, bear that in mind. This is nothing but a communication or electrical signaling mechanism for neurons and other excitable cells such as muscle. And so the action potential starts at the soma, where those signals are perceived onto that neuron, and they travel along the length of the axon all the way to the axon terminal. And then from there, they then trigger another type of communication to another neuron. Okay? And so the events that we spoke about in terms of the action potential were the depolarization, that's the first part of the action potential. Then there's the repolarization, which happens via the potassium channels. And then there's a slight period of hyperpolarization that we'll speak about.